My name is Min-Woong from Shizuoka University. Today my talk title is the low noise high sensitivity CMOS image sensors for scientific and industrial applications. Actually, there's some techniques used for the developed image sensors are not new technologies. This is improved version of our previous work. So today in my presentations, I will focus on the improved performance of the sensors by using several method and the process optimization. And this slide shows the outline of my talk today, and the first introductions, and then I will introduce several examples for the scientific applications with some requirements. And then I will explain about the low noise column, the parallel, this is actually the readout circuit, very briefly, because this is one of the key technologies for reducing the noise. And then the results are shown, and finally I will conclude my presentations with the brief summary. Here is several of the example of the scientific imaging. The first, this is the cancer cells taken by some very high performance CCD camera. For taking this image, we require the very high sensitivity, the factor parameters. And the next thing is the space imaging. This image is taken by the NASA's scientific imaging system, so-called OSIRIS. And it's also required the high sensitivities, and especially the wide spectral range is also needed. And third thing is the nearest imaging. This means the near infrared spectroscopy. This nearest imaging is this system, the measurement system is simply composed of the source part. The source means light source part, and the detector. And incident the light from here into some skin or the brain, and this signal is absorbed or some diffused. So this absorbed or some diffused signal is detected by the detector. So for realizing that the nearest imaging, we require the low noise and the high sensitivity. So I briefly categorized some requirements for the scientific imaging. And the first is the low noise. Actually, when we observe some very weak signals, it's very difficult to distinguish the real signal and the noise level. But with background noise or some noise levels can be reduced, we can obtain the very clear image information without loss, even though the very weak signal. And next thing is the high sensitivity and the WDR wide dynamic range of sensors. Actually, this image, the captured image is not good for introduce these parameters, but I just introduced the concept of the WDR. Yes. So for scientific the applications that will require the high sensitivities and the WDRs of the sensor itself. And third thing is the wide spectral range and the sensitivities. For observing some invisible areas such as the UV and the X-rays and some near infrared part, as well as of course the visible area. And first thing is the high conversion gain is very close to, this means it's very close to the low noise and the high sensitivities. And the final thing is operation speed. It's very important because for realizing some real-time measurement system. So these requirements, our research goal is set it. The first is the low noise performance, below the 1 electrons, and then the high quantum efficiencies and the wide spectral range, and finally high conversion gain. This slide shows the high performance column parallel ADCs, we so-called the folding integration cyclic ADC. So this is very important, the techniques for our developed sensor. So I just briefly explained. Simply, we can divide the operation mode two. The one is the folding integration ADC, and the second thing is the other thing is the cyclic ADC mode. And the first, this blue line, this is the folding integration mode. For the folding integration mode, and by multiple sampling techniques, we can improve the SANR of the sensor. And this circuit configuration is the move to the cyclic ADC mode. This one. It's almost same. Analog cover is not changed. Just change the sampling path, not from the pixel, just the feedback from analog output node of the analog cover. Actually, I prepared another slide, but I just skipped. Basically, we can divide the two page types. First is the sampling page and the charge transfer page. So for obtaining the multiple bit, these operations are repeated several times, several cycles. And most important thing, actually, by using the multiple sampling techniques, we can reduce the noise level, and simultaneously, by the folding the operations, we can increase the operation range, dynamic range of the sensor. That is an important point. And this is our developed CMOS cameras. The cover is open now. And this is developed image sensor. And this chip block diagram. Our sensor is implemented by the 1 poly formatter, a 0.1 micrometer standard CIS process. Total number of pixels is 1024 times 1024, and pixel size is quite large for encouraging some sensitivity, and the 11.2 micrometer times 11.2 micrometers, and the fill factor is 44%. And this is a measure of the random and the potential noise as function of the signal levels. As can be seen from this result, our sensor's conversion gain is 124 microvolt per electron. It's very enough for achieving the large signal. This slide shows the dark leakage current. The level is the 7.55 electron per sec. This is the median value, and it is correspond to the current density of the 0.96 picoampere per centimeter square. This is quite good, the result of the sensor. And this slide shows the measure of quantum efficiency. Actually, we modify the doping concentration of the epitaxial layer for expanding the spectral range. So as a result, we can get the better the result compared with the previous one, but not significantly, dramatically improved. But this characteristic is enough for applying the imaging applications. And this slide shows the captured image by our developed sensor. as you know, this one now this is very dark scene, 0.01 lux. But using our developed sensor, the image, the targeted object is clearly represented. So I changed the illumination conditions from the 0.01 lux to the 0.001 lux. This is 10 times smaller than this illumination condition. Of course, this white speck is increased, but this is very dark scene. So, but we can obtain the very clear image from the some targeted object by using our developed sensor. And this is the sensor's performance and the characteristics. The almost parameters we already mentioned. The sensitivity is 87 volt per lux second, and the dynamic range of 70.5 decibel. It's enough for the scientific image sensor, I think. And I would like to summarize in this slide. By optimizing the doping profile and the pixel design for the detector, the image sensor has been achieved a very low noise level, actually. That this is implanted noise of the 1.17 electron, and low dark current and high conversion gain and high quantum efficiency. From these results of the image sensors, we confirm that the developed image sensor can be sufficiently used for the scientific or industrial applications. Thank you very much.